Good afternoon, everyone. We're going to go ahead and get started talking about chemical kinetics or reaction rates and how we can sort of manipulate and control how reactions occur and what's going to happen. So, we're going to start off with a little bit of a review. Now, at the end of the last unit, we identified a couple of different parts for a potential energy diagram. We looked at the potential energy of reactants, so it's usually found at the very beginning here. This is how much energy is stored in the bonds at the beginning. We then have this climb where we make our way up to the top. This was our activated complex. The amount of energy to reach there was our activation energy. And then after we've crossed that point, that transition point, then we had what we call our potential energy of our products. This allowed us to go ahead and see how energy changes different forms and gets stored in different ways as we continue through a reaction. The last piece of the puzzle that we sort of looked with and we sort of dealt with in terms of endothermic versus exothermic is the enthalpy change, or the energy change for the overall system. So, since I'm looking at here, this is where I began and this is the energy where I ended. The difference between these shows me that I gained energy. So we would say that this was an endothermic reaction or endothermic process. Now, with thermochemistry, we talk about the beginning and the end. When we talk about kinetics, now we're going to focus mainly on this middle part and how we can adjust and sort of play around with it. So, first thing we need to know, what is the rate of reaction? Rate of reaction is going to be us looking at how the concentration or molarity, remember we did some practice with that, changes over a period of time. The easy way I think about it is the speed of the reaction. If I wanted to look at, someone running, say a mile, I'm going to look at how long it took them to reach that distance. In terms of reaction, we want to look at how the concentration or the amount of our reactants, amount of time it takes it to turn into the products. And then from this, we can make some sort of different ideas. Now, one of the ways that we write this is what we write a rate law or a rate equation. This is going to show us how the reactants themselves actually play a role in determining how fast the reaction is. We have a couple of basic things that we're going to look at. We're not going to get too deep into it, but you will at least have one question that deals with writing a rate law. And it's very, very simple because we get to use some simple information, as you'll see on the next screen. Now, the general form is going to be rate. So we always start with rate equals K, lowercase k, times the concentration of whatever substance you have, times the concentration of the other. This is giving you a little bit of a breakdown and showing that it's going to be the concentration of the actual reactants themselves. Lowercase k is a rate constant. Again, we're going to be figuring this out experimentally, so don't worry, it's not something you have to calculate for this test, but just have an idea that these two things sort of play a major role. Now, what do we do with the coefficients? Well, if we look at coefficients in a reaction, they tell us how many of the molecules happen to be there, but they also tell us how fast they react compared to the other. What do I mean? Well, in order to make C and D here, I have A with 2 molecules of B. This means that B happens to go twice as fast as A would. This is going to help us to understand, if we're looking at how things change over a period of time, how much of B should be available at a given point. And of course, these are our basic units. Now, what are the factors that are going to affect the reaction rate? Because we have a couple things we need to pay attention to here. You want to make sure to write these down. Well, the first thing that we need to look at is collision theory. What causes a reaction? Well, major ideas are, 1, they have to collide. I think that's kind of self-explanatory. 2, they have to be oriented in such a way that they can actually bond and break bonds. And there's a short video clip I'll show you in class that'll sort of help to make this a little bit clearer. And last but not least, they have to have enough energy to do something, to actually react. The way I think of this is, I know when I was younger we used to play a game called Red Rover. Well, in Red Rover send so and so over, and they have to run and they have to try to break through the arms of the other person. Well, if they don't run with enough energy, they don't break the bonds, or they don't break the people's grip, and that way they don't get through. They can't join that side. This is the same situation here. Not only do they have to collide, not only do they have to be arranged in a certain way, but then there also has to be enough energy so that we can actually break and form new bonds from that interaction. This is going to allow us to get closer and closer to that thing we call activation energy. Now, if you remember, we talked about activation energy as the amount of energy it takes to go from our starting point to the highest point of our graph, our activated complex. This is going to be that energy barrier. This is going to allow us to be able to see how much energy we have to put in just to get the reaction started. The larger this value at the beginning, the less likely the reaction is to happen without a lot of energy input. But if I was looking at it the opposite way, it requires a lot less energy. Now, the other factors that we need to pay attention to, we say the nature of reactant substances. A couple things to consider. Do they have charges? If there are charges, most likely they're going to attract each other and they're going to react faster. Are there a lot of bonds to be broken and formed? Are the bonds that are being broken and formed weak or strong? The stronger they are, the more energy it's going to take. To give you an idea, methane. Many of you have gas stoves at home. If I have a gas stove, it's using methane to cook. It burns very, very fast and there's no real loss of time in between. Whereas if I'm looking at something like photosynthesis, which we've heard about for years in biology, this is a process that takes several days, many times, sometimes hours or so forth. So the types of substances that are interacting are definitely going to affect the rate of reaction. The next thing we need to look at is the size of the particles. Now, the basic idea is if I have a big, huge chunk of iron and it's going to start reacting with a solution, where these two things come into contact is where the reaction is going to occur. So I can't have anything reacting on the inside of the iron if there's nothing there to react with it. If we can increase the surface area by doing something like grinding it up or drilling it down, then we can increase the amount of collisions. If we increase the number of collisions, this goes back to our collision theory. Increase the number of collisions, a better chance that we have enough energy, right orientation, and so forth. Now, to give the idea, if you have coal dust and you light it, it's very, very explosive and you can hurt yourself really, really bad. But if I were to go and get a lump of charcoal or coal in general, it burns very, very slowly. This is because of the surface area that the oxygen and the flame are actually allowed to interact with. The next thing we want to look at is the temperature. Now, if you remember when we talked about gases, we said that the kinetic energy of the particles is directly related to the temperature. So, if I increase the temperature, that means there's more energy in the particles. Well, if there's more energy in the particles, there's a better chance for collisions, better chance that we're going to reach that activation energy. And this is a constant theme that we see throughout kinetics. The whole goal of everything is how can we increase the number of collisions, the amount of energy to better reach that point of activation energy and get to that activated complex. Another thing that we're going to consider are the concentration of reactants. What do I mean the concentration? Well, how many of the particles are actually there to interact? If there are only 5 particles there to interact, there's going to be less likely to have a collision. But if I have 105, there's so much more. Now, the example that's given here is combustion in pure oxygen versus air. Well, in pure oxygen, I have nothing but oxygen molecules. So if I burn something, it's going to interact that much more. Whereas in air, I'm looking at all the gases that are there at maybe about 20 to 21%. So the oxygen amount is much, much less, and so it's going to slow down the process. Last but not least, we need to look at using a catalyst. Now, A catalyst is not used up by the actual reaction. It's there, but it's not involved. All it does is it lowers the activation energy. So if you're looking at the graph here, this may have been the activation energy at the very, very beginning. Notice how far it is over. It requires a whole lot of energy to get particles back here. Because of that, we're noticing that only a few are able to make it through. But if we were to go ahead and change it, and we add in our catalyst, our activation energy is now way back here. Look at the amount of our particles that are able to make it past that point and to actually form our products. This is the goal that we've always looked for. This is actually where we're going to go ahead and wrap up the first video. Now, make sure that you go back, you review your notes, and be ready to work on it. Have a great afternoon, and I'll see you in class.